Up till now, we discussed the analysis of transmission lines. We derived the transmission line equations, also studied the power flow on transmission lines, voltage and current wave characteristics on transmission lines, and later we developed the graphical tool for carrying out the analysis of transmission lines. Now we discuss the applications of transmission lines in high frequency circuits. Although originally transmission lines were proposed for transferring power from one point to another efficiently, people have found many other applications for transmission line sections. When you go to high frequencies, in fact, many of the reactive circuit elements are replaced by transmission line sections. So now onwards, we discuss some of the important applications of transmission lines. The first application of transmission lines is in the measurement of high frequency impedances. If you recall, I had mentioned that when you go to high frequencies, the measurement of phase is a very tedious task. You can measure the amplitude of a signal rather reliably, but the measurement of phase is rather unreliable. For measurement of complex impedances, we have to measure the complex voltage and complex currents, and since the measurement of phase is not that simple, the measurement of complex impedance becomes very difficult at high frequencies. However, we have seen from transmission lines that the phase, which is the temporal phase between the voltage and current, gets translated into the spatial phase in the form of standing wave patterns, and therefore we can estimate the temporal phase between the voltage and current by indirect means, that is by measuring the standing wave patterns on the transmission lines. Precisely that is what we use for measuring the unknown impedances at high frequencies using a transmission line. For this purpose, we use a transmission line which is of special type, what is called a slotted transmission line. In fact, this transmission line has a groove cut along the length of the transmission line, so that we can measure the voltage variation along the transmission line. Again, when we are doing the voltage measurement, we are measuring only the magnitude of the voltage along the transmission line. So there is a probe, which is a voltage probe, which slides along the transmission lines and measure the magnitude variation of the voltage along the transmission line. So this probe measures the voltage along the transmission line. This line is the slotted transmission line. Now for measurement of the unknown impedance, we connect the voltage source at one end of the slotted transmission line and connect the unknown impedance which we want to measure to the other end of the transmission line. In general, the voltage standing wave will be created on this transmission line, and by moving the voltage probe along the transmission line, we can measure the magnitude of the voltage. If you plot the variation of magnitude of voltage along the transmission line, we get this voltage standing wave pattern. Now, as we have seen earlier, that the distance between two voltage maxima or two voltage minima is equal to lambda by 2. So, by measuring the separation between the two maxima point or two minima point on the transmission line, we can estimate the value of the wavelength. Once we get the wavelength, we can find the value of beta, which is 2 pi divided by wavelength. So, the first step in measurement of impedance is you find out the voltage standing wave pattern, identify the location of the voltage maxima or voltage minima, find the distance between the two adjacent voltage minima or voltage maxima, find the value of lambda by 2, and from here you find out the phase constant beta. The second step would be to find out the location of the voltage maximum on the standing wave. So, let us say if I measure from the load end, the voltage minimum occurs at a distance L minimum from the load point. Also, we can measure the value of the maximum voltage and the minimum voltage on the line. So, I can get mod V maximum, I can get mod V minimum on the transmission line. So, I have measured now the propagation constant or the phase constant beta on transmission line, measured the maximum and minimum voltage on transmission line, and also the location of the voltage minimum on transmission line. Once I do these measurements, then now I can find out the parameter which are required for the impedance calculations. The first quantity which you now calculate is the VSWR for this load. As we have seen, the VSWR rho is mod of V maximum divided by mod of V minimum. So, once you do the measurement of the maximum and minimum voltage, we can calculate this quantity rho. Once you get the VSWR rho, we now know the maximum and minimum impedance which one can see on transmission line. So, at a location where the voltage is minimum, that is this location, here now the impedance will be the minimum impedance, and that will be R min, and as we have seen earlier that R min is equal to Z0 divided by the VSWR. So, I know the impedance at this location here, that is Z0 divided by the VSWR. So, from here I now calculate the quantity R min, that is the characteristic impedance divided by the VSWR rho. Once I know the impedance at this location, then the calculation of unknown impedance is simply a impedance transformation problem. If you recall, we had said if we know the impedance at any point on transmission line, we can find the impedance at any other point on transmission line by using the impedance transformation relation. So, in this case, now we know the value of the impedance at this location, which is Z0 by rho. Once I know this, I know the distance of this thing from the load, which is L min. So, I can transform this impedance by a distance L min away from the generator, so that the impedance is equal to ZL. So, in fact, ZL, the unknown impedance, is nothing but the transformed version of Z0 by rho by a distance L min away from the generator. So, the ZL now calculation is straightforward. So, ZL is equal to, you apply the transformation relation. So, you have here R min cosine of beta into the distance, and keep in mind here we are having a distance now away from the generator, because we are transforming this impedance away from the generator. So, the distance is negative. So, you have L min, which is negative in this case. So, this will be cosine of minus beta L min plus j Z0 sine of minus beta L min divided by Z0 cosine of minus beta L min plus R min sine of minus beta j here L. So, the unknown impedance now is a transformed version of R min away from the generator. So, the distance is negative. So, the L min is negative. Once you get this, now finding out ZL is a matter of simply separate out the real and imaginary parts. So, if I separate out the real and imaginary parts, I get explicitly the value of the resistance and the reactance as, so I get the unknown impedance now Z, which is ZL is R plus jx, where R will be equal to rho into 1 plus tan square beta L min divided by rho square plus 10 square beta L min, and the reactive part x will be equal to 1 minus rho square tan beta L min divided by rho square plus tan square beta L min. This is nothing but the real and imaginary part of this. So, by rationalizing this function, we can separate out the real and imaginary parts. So, the real part gives me the resistive value of the unknown impedance, the imaginary part gives me the reactive value of the unknown impedance. So, by transforming the impedance R minimum to the location of the unknown impedance, we get the complex impedance. So, once you measure the VSWR on the line and the location of the minimum, then finding out the unknown impedance is extremely straightforward. However, when we go into the practice, we will see that while connecting the unknown impedance to the slotted line section, we use some connectors and other things, and because of this the location of the impedance is not that accurately known. So, measurement of L min sometimes becomes unreliable in some sense. So, if I knew L min very precisely, then of course the transformation is very accurate and you can find out what the unknown impedance is. But if L min is not known, then you will have an error in the estimation of the unknown impedance. So, normally what people do is to define the location of the load. First you replace the load by a short circuit, do the measurement on the transmission line, find out the location of the voltage minimum with the line terminated in a short circuit. Then you replace the short circuit by the load and now find out the standing wave pattern with the load. So, we have two standing wave patterns measured on transmission line, one with the line terminated in a short circuit and other one the line terminated in the actual load which you want to measure. So, in first case, when let us say this is the transmission line and this is the plane at which I can connect either the load or the unknown impedance. When I connect the short circuit at this location, the standing wave pattern will have a voltage minimum at this location, and since this is the ideal short circuit, the VSWR for this will be infinity, the minimum voltage will be 0. So, if I plot the standing wave pattern in this case, the standing wave pattern will look like that. So, the voltage is minimum, there will be a maximum voltage. So, the ratio of maximum to minimum voltage is infinity. So, you have VSWR infinity. This is the voltage standing wave pattern for the short circuit condition. So, this is the short circuit load. Now, I replace this load by the actual load on the transmission line. Two things will happen. The voltage standing wave pattern in general will be shifted with respect to the short circuited standing wave pattern, and also the VSWR are not infinity. So, V minimum voltage will not be 0. So, in general we might get a voltage standing wave pattern which will look something like that. So, I may not have now a maxima and minima of the short circuited pattern and this pattern at the same location. So, I have two patterns here. This is for the load, this is for short circuit. This is the location now at which either the load is connected or the short circuit impedance is connected. As we know now that the location which is at this location has been repeated at every lambda by 2 distance. So, whether I do the measurement at this point or I do the measurement at this point or this point, they are identical because the impedance characteristic repeat every lambda by 2 distance. So, now once I find out the minimum point for the transmission line when it is terminated in the short circuit, I know precisely the location of this point because separation between this point and this point is lambda by 2. So, instead of doing the measurement from this point, I can do the measurement from this point, which is very well identified on the slotted transmission line. So, I can do the measurement of this location from the minimum which I see from the standing wave of the unknown load. So, essentially distance from here to here, this distance is nothing but L min. So, now without worrying about what I am connecting to the transmission line, as long as I can connect a short circuit impedance at a location where the unknown impedance is connected, I can precisely find out the value of the L min. And once I know L min, then I can go back and substitute into that formula and find out what is the unknown impedance. So, in practice, whenever we are doing the measurement of unknown impedances, we have to do the measurement of standing wave pattern twice, once by short circuiting the line and later by connecting the unknown impedance at that location, and then by doing the measurement of L min from the relative patterns of the short circuited standing wave patterns and the unknown impedance standing wave pattern, we estimate the value of L min. So, this technique for impedance measurement at high frequency is very useful, and in fact, if you go to frequencies like microwave frequencies, without the measurement something like this on the slotted line, one will not be able to measure the unknown impedances. So, at high frequency, the transmission lines come out very handy for measurement of the unknown impedance. The second application which we have for the transmission line is the circuit element, use of transmission line sections as a circuit element. As we increase the frequency, as we have seen earlier, the distributed element starts showing its effect. So, let us take an example. Suppose I wind an inductance to be used at very high frequencies. So, let us say I take a coil or I take a wire and make a coil out of it to make an inductance. So, let us say I make an inductance to be used at very high frequencies. I can calculate the value of the inductances by the relations which are available. However, what we do not take into consideration is the capacitance between the windings of this inductor. So, you also have the capacitances which are distributed capacitances between the turns of the inductances. As the frequency increases, the effect of these capacitances also start showing, and one can show that for typical inductance which you wind, the resonant frequency lies for the distributed capacitances and the inductance which you have wound typically in the range of about 100 to few hundred megahertz. That means, if I wind an inductance beyond about few hundred megahertz, the inductance will not behave like an inductance. It will rather behave like a capacitance because we have already crossed the resonant frequencies. So, the effect of capacitance now is more dominant compared to the inductance. Similarly, suppose I have make a capacitance at low frequencies, it behaves like a capacitance, but as I increase the frequency, we have this leads which have inductance, and again as the frequency increases, this inductance effect starts dominating. So, beyond certain frequencies, the capacitance does not behave like a capacitance, it rather starts behaving like an inductance. So, if we make an inductor at low frequency, we can reliably design the inductor but when you go to high frequencies, its reliability is very poor, because the inductor might start behaving like a capacitance. Similarly, if I have a capacitance to operate at low frequencies, it works reliably, but when I increase the frequency, the lead inductances of the capacitance start dominating, and it is possible that the capacitance will appear like an inductance. So, realizing a reactive element at high frequency is not that easy, because we do not have a reliable circuit element which will be guaranteedly used like an inductance or like a capacitance. At the same time, when the frequency is increasing, the wavelength is becoming smaller and smaller, and as we have seen earlier, that if you consider the short circuit or open circuit line, the input impedance of these lines behave like a reactance. So, when the frequency increases and the wavelength becomes smaller, the size of the section of a transmission line which can give you impedance which is reactive, that becomes more and more physically realizable. So, you are having two things now working in the favor of transmission lines. The lumped circuit elements are becoming more and more difficult to be realized at high frequencies, and realization of the reactances by using transmission line section is becoming easier, because the wavelength is becoming smaller and smaller. So, sections of the transmission lines now are becoming more physically realizable, their size is more accommodatable. So, these two factors essentially support the use of transmission line section for realizing the reactive elements in the high frequency circuits. And in fact, if you go to a typical high frequency circuit of few hundreds of megahertz or few gigahertz, most of the reactances in the circuits are replaced by the sections of transmission lines. So, let us see how the transmission line section can be used as a reactive element. So, let us consider section of a transmission line. Let us take this section of a transmission line which can be either short circuited or open circuited. Now, if I go to the Smith chart, and if I consider this Smith chart as the impedance Smith chart, I know that this point here, the rightmost point, represents the open circuit on the transmission line, and this point here represents the short circuit on the transmission line. So, for a open circuit or short circuit load on the transmission line, as I move now on the transmission line towards the generator, I move on the outermost circle of the Smith chart. And if you recall, for the outermost circle on the Smith chart, R is identically 0. So, it represents only pure reactive impedances on the outermost circle of the Smith chart. So, for a load of short circuit or open circuit, by using different lengths of transmission line, I can get different reactances as the input. So, precisely that's what the idea is, that you take a transmission line, terminate this transmission line into the short circuit or open circuit. The input impedance, if you measure for these sections of transmission line, they will ideally be reactive impedances. So, by changing the length of the sections of transmission line, I can realize a reactance between these terminals. So, wherever I want to connect a reactive element, I simply connect a section of a transmission line at that location, and this section of a transmission line will appear like an appropriate reactance at that location. Let us elaborate on this idea and ask what would be the lengths of the sections of transmission lines, right, so that we can realize the particular reactances on the transmission line. If we do analytically, then the input impedance of a section of a transmission line Zn, that will be J into Z0 tan of beta L. This is if the line is short circuited, and will be equal to minus J Z0 cot of beta L if the line is open circuit. Getting this is very straightforward. In the impedance transformation relationship, if I put the load impedance 0 for the short circuit case, I get the Zin, which is the transform impedance over a length L towards the generator, that will be the input impedance. If I take the open circuited line, then I put load impedance equal to infinity, then over a distance L towards the generator, I get the input impedance which will be given by that. So now the problem for realization of a given reactance is just to find out what is the length of this section of a transmission line, which will realize that reactance in which we are interested in. Let us say the open circuited, short circuited line and open circuited line lengths are denoted by LSC and LOC. And let us say I want to realize certain reactance X. So for the short circuit case, from here X will be equal to Z0 into tan beta L SC for short circuit case, and X will be equal to minus Z0 cot of beta LOC. I can invert this relationship to find out the value of LSC, because the phase constant beta on the transmission line section is known. So if I know the frequency of operation, if I know the velocity of the wave on the transmission line, I can find out what is the value of lambda. Once I know the value of lambda, I can find out what is the phase constant. Once I know the value of beta, I can invert this relation and find out what is the value of the length of the sections of transmission line, if the line is short circuited or if the line is open circuited. So by using now the sections of the transmission lines, I can realize an unknown reactance on the transmission line. Now for doing these calculations also, the use of Smith chart comes out very handy. But before I get into that, let us see that this function which we are having here, the tan function or the cot functions, for the variation of beta LC from 0 to 2 pi, any of these functions vary from minus infinity to infinity. So that means if I change the value of LC or OC transmitted lines, then I can realize any arbitrary value of the reactance. There is absolutely no limit. So any arbitrary value of reactance between minus infinity to plus infinity can be realized either by using short circuited line or by using open circuited line. So the choice which one to be used, whether short circuit line to be used or open circuit line to be used, will depend upon the system in which you want to employ this circuit element. Let us take a simple example. Suppose I have a parallel wire transmission line, then connecting two ends of the transmission line is rather very easy. So I can short the end of the transmission line. So in those structures, parallel wire structures, where connecting the two ends of wire is easy, we prefer to use the short circuited end of the transmission line. However, if I consider a line like something on printed board, so there is a ground plane on one side and the line on the other side. For short circuiting this line, we have to drill a hole into the printed circuit board. So realizing a short circuited line in that configuration is rather difficult. So we prefer to use an open circuited line. So there may be situations where the short circuited transmission line will be preferred or the open circuited line will be preferred. And as we saw, irrespective of whether we use short circuited line or open circuited line, we will be able to realize all the reactances from minus infinity to plus infinity. That means we can realize any capacitive or inductive reactance by using an open circuited or a short circuited section of a transmission line. Now how do we find out the lengths for getting the open circuited or short circuited section of a transmission line. Firstly, we will note here that to calculate that length, the problem now is opposite of impedance calculation. What we are saying is generator is again on the left side, this is the load end. I know the value of the reactance at this location, I know the value of impedance at this location, which is either short circuit or open circuit, and I want to find out what should be this distance. So the impedances are known and the transformation length is to be found out. So the problem is on the Smith chart, if I can mark this impedance Jx and ask a question, how much should I move away from the generator so that I reach to a location short circuit or open circuit. So the problem here now is, after we mark the reactance on the Smith chart, find the length so that we reach to the short circuit point or open circuit point. Let us say I want to find out some reactance x which lies somewhere here. Note again, this point is lying on the outermost circle of the Smith chart. So this is the reactance which is Jx, which we want to find out. Now, as we have seen, if we are treating this chart as the impedance chart, since the point is lying on the upper half, we want to realize the reactance which is the inductive reactance. Note here, though the reactance is inductive, we are not realizing an inductance. When you go to low frequencies, we realize an inductance and a capacitance. Here we are directly realizing the reactances. So this is the quantity which is the inductive reactance we want to realize at a particular location at a given frequency. Now, if I move from this reactance point away from the generator such that I reach to the short circuit point or open circuit point. So if I move now away from the generator, and that is in the anti-clockwise direction, because on the Smith chart clockwise movements are towards the generator. Now we want to move away from the generator. From this reactance we want to move away from the generator till I reach to the short circuit point, away from the generator till I reach to the open circuit point. So now if I move away from the generator in the anti-clockwise direction till I reach to the short circuit point, which is this point is short circuit and this point is open circuit. So if I find out this length corresponds to the length of a transmission line LSC. Similarly, if I move up to the open circuit point in the anti-clockwise direction, that is the length which will give me LOC. So to realize this reactance X here, if I take this arc represents LSC, and if I take an arc which is from this point all the way up to this location, that will represent LOC. So let me repeat, how do you find out the length of the short circuited or open circuited lines for realizing a reactance? Take the value of the reactance, mark it on the Smith chart. Remember, on the Smith chart we always have the values which are normalized. So this reactance here is a normalized quantity. So let me denote that specifically as X bar. So the first step is, whatever reactance you want to realize, convert that into a normalized reactance, mark that normalized reactance on the Smith chart, move in the anti-clockwise direction to this point, the leftmost point on the Smith chart. That gives me the length which is the length of the short circuited line, LSC. The LOC I can find out either by adding to LSC lambda by 4, because we know that these 2 points are separated by a distance of lambda by 4, or I can measure this length from all the way from here to here, that will give me the open circuited length of the transmission line section. So, depending upon the choice of the circuit, we can either have a section of a line which is open circuited or short circuited, and we can realize that for any arbitrary inductance or capacitance on the transmission line. Now, if I look at this carefully, as we have already seen that any length of a transmission line can behave like a capacitance or inductance, because depending upon the length I can get reactive element which will be like a capacitance or which will be like an inductance. So, let us say suppose I take a short circuited line. So, the load impedance is somewhere here. If I move now towards the generator, that means in the clockwise direction, up to a length of lambda by 4, the input impedance will be an inductive impedance. Beyond lambda by 4 to lambda by 2, the impedance seen at the terminals of the line will be a capacitive impedance. So, a short circuited line, if the length lies between 0 and lambda by 4, it will behave like inductance. If the length lies between lambda by 4 and lambda by 2, it will behave like a capacitance, and so on. Similarly, if I consider a line which is open circuited, then the movement towards the generator for first lambda by 4, the reactances will lie in this. So, an open circuited line of length from 0 to lambda by 4 will behave like a capacitance, from lambda by 4 to lambda by 2 will behave like an inductance, and so on. So, now depending upon the length of the transmission line, I can get a inductive behavior or I can get a capacitive behavior. I can write this thing rather explicitly, and that is, I have a situation, this is the short circuited line where LSC is between lambda by 4 and 0. This line, as we saw, is a short circuited line. So, between lambda by 4 and 0, this is equivalent to an inductance. So, this line is equivalent to a inductance. If I take a line short circuited whose length LSC lies between lambda by 2 and lambda by 4, then from here now the length is in this region. So, that will represent a capacitance. So, this line will appear like a capacitance. Similarly, an open circuited line LOC, if it is between lambda by 4 and 0, then this is equal to a capacitance, and if the length is between lambda by 4 and lambda by 2, then this is equivalent to an inductance. So, now any section of a transmission line of size from 0 to lambda by 2 can realize any arbitrary value of capacitance and inductance at a given frequency. So, let me again mention, we are not realizing a inductance and capacitance, we are realizing the inductive or capacitive reactance, and then equivalently we can say that that reactance is having that capacitance or that inductance. Now, once we are having a value of capacitance or inductance, take a case like this. Up to lambda by 4, this behaves like a capacitance. From lambda by 4 to lambda by 2, it starts behaving like an inductance. So that at lambda by 4, the behavior of this line changes from capacitance to inductance. So at that location, at lambda by 4, you have a characteristic which is more like a resonant line characteristic. So if I take a resonant circuit, LC resonant circuit, then at resonant frequency, on one side of which you have inductive behavior and other side of which you have capacitive behavior. So if I go to a section of a line which is lambda by 4 or lambda by 2, then at that frequency the line will behave like a resonant circuit. So section of a line may not be used only like a reactive element, but it is possible to use the section of a line like a resonant LC circuit also. So now we see that suppose we take a line around the length of lambda by 4 or lambda by 2, then they will have a behavior similar to the LC resonant circuits. Let us consider a line which is a short circuited line, and now ask, if I change the frequency for keeping the length of the line fixed, if I change the frequency, how the behavior of the reactance is going to change? So as I change the frequency for a given length of the line, the impedance seen between the terminals of the line is going to change. So I get a characteristic for any length, typically say length of the line, which will look something like that. Go like this, go like this, and so on. So if I take a line, let us say short circuited line, and if the length is equal to lambda by 2, since this is short circuit, the impedance will be equal to 0. Then the impedance will change, and when I reach to a point around lambda by 4, that time this line will appear open circuit at this location. So the impedance will become equal to infinity. One side of that frequency will be capacitive, the other side will be negative. So when the frequency is such that this length is 0 or lambda by 2 or lambda, I get the impedance which will be here or here or here, because the impedance seen between the input terminals is 0. However, if I go to the frequency for which the length is equal to lambda by 4, then the impedance seen between the terminals of the line is infinity, because this will appear like an open circuit. So I will see a location somewhere here. So as I change the frequency for a given length of line, when the length of the line becomes 0 or lambda by 2 or lambda, then I see the impedances which are here or here or here. If I go to the frequency for which the line length becomes lambda by 4 or 3 lambda by 4 or 5 lambda by 4, then I will see this point, this point, this point. That means in a frequency range close to this, this is characteristic is very similar to a series LC circuit, series resonant circuit. Whereas if I am in the vicinity of this frequency, then the behavior of a transmission line is similar to a parallel resonant circuit. Because if I take a characteristic of series and parallel resonant circuit, we know for a series circuit, the impedance variation for this will be something like that. This is the frequency which is the resonant frequency of your circuit F0. So this is the frequency plotting, this is the mod of x if you plot, not mod of x, you have to plot x where you are plotting negative values. So if I plot the reactance as a function of frequency for this circuit at resonance, the reactance is 0. As you increase the frequency, this becomes larger. So, you see the inductive reactance. If you decrease the frequency, this reactance is larger. So, you see capacitive reactance. So, a behavior crossing through 0 is a characteristic of a series resonant circuit. So, this circuit is a resonant circuit which is series. On the other hand, if I consider a circuit which is a parallel resonant circuit, then the frequency characteristic for this, the frequency, this is x, this will be, because at the resonant frequency the reactance will become infinity, this will act like open circuit, and as I go away from the frequency, on one side you will see the inductive effect, the other side you will see capacitive effect. This frequency is your f naught. So, a line can behave like a series resonant circuit if I go to a frequency where the frequency characteristic is like this, or it can behave like a parallel resonant circuit if I go to a frequency around which the frequency characteristic is like that. So, for a given length of a transmission line, those frequencies for which the length of the line is close to lambda by 2, the line will behave like a series resonant circuit. On the other hand, for those frequencies for which the length of the line is around lambda by 4, this line will behave like a parallel resonant circuit. This is for short circuited case. Exactly opposite will happen for the open circuited case, that for an open circuited line, for length of the line around lambda by 4, the line will behave like a parallel resonant circuit, because the input impedance will be infinity. So, in this case, when the line length is about lambda by 4, this will appear short circuit, so it will behave like a series resonant circuit, and if the length of the line is lambda by 2, then the line will behave like a parallel resonant circuit. So, depending upon whether I am using a short circuit or open circuit, I can realize the series or parallel resonant circuit at different frequencies. So, invariably when we go to high frequencies, the line can be realized for getting reactive elements into the circuit. The line can be used for realizing the series or parallel resonant circuit into a high frequency circuit. Whenever we are having a resonant circuit, the immediate question one can ask is, what is the quality factor of a resonant circuit? Because a resonant circuit is always characterized by its quality factor. If you recall from the very basic definition of the quality factor, the quality factor is related to the losses into the circuit. Higher the loss, smaller is the quality factor. So, whenever we have a reactive element like a inductor or capacitance, the losses into these elements characterize the quality factor. In this case, however, when we are doing a transmission line, we have treated this transmission line as a lossless transmission line. So, by definition, the quality factor for these resonant circuits is infinity, because there is no loss. However, in practice, there is always a small loss in the transmission line, and up till now we have treated the transmission line, low loss transmission line, as a lossless transmission line, because we were not really interested in the small loss. However, if we treat now the line as the lossless transmission line, we will not get the answer for the quality factor, because the quality factor will be always infinity. So, in this case, when we are interested now in finding out the quality factor of the resonant circuit, no matter how small the loss of the transmission line is, we have to include the loss of the transmission line, and then we can calculate the quality factor. So, we will continue the analysis of the resonant transmission lines and we will calculate the quality factor of the transmission lines. And then we will also see that these resonant sections of transmission lines can be used for other applications, that is for stepping up the voltages or currents in the high frequency circuits. So, the sections of transmission lines can also be used as the voltage or current stepping up transformers, apart from its use as the reactive circuit elements and the resonant circuit element.